Hi everyone, I'm Aditya Balu, and now I will be covering about the seventh session of this tutorial on physics-based inverse solvers. Uh, a quick outline of what I would be presenting in this session is I'll first give a brief recap on the scientific machine learning area which we have covered and all the works and the terminologies we have used in this area. And then we will take some preliminaries of generative adversarial networks, which we'll be using in this inverse solvers framework. And for this purpose, we explain a framework called InvNets, where we take physics consistent generative models for inverse problems. And then we'll give some concluding remarks. So a brief recap of scientific machine learning, or SciML. As we explained in the beginning of this tutorial, scientific machine learning has two broad applications. One is the forward problems, where you're assimilating physics information from partially observed data. And the other application is inverse problems, where you're performing physics-based design of systems. Both the systems require physics-based surrogate neural networks, and we have covered in the past session 3 and 4 on how physics-informed neural networks is one particular approach which you can use for representing neural surrogates or physics-based surrogates. And the other approach which we learned in session 5 and 6 is grid-based, either finite element or finite difference-based neural PD surrogates, where you take a grid of points, and then for this grid, mesh grid of points, you predict the solution of the physics, and then you train the models. Both these approaches are really well, but in both the approaches, what we do is we take in a set of known parameters and then obtain a set of unknown parameters for a PDE, and we perform a very straightforward finite element residual minimization. However, inverse problems are slightly different than that. In order to tackle some inverse problems, we'll look at some preliminaries of how we train generative adversarial networks. First of all, let us understand, why do we need generative models? So here's a problem which our research group has been working on in terms of why, which motivates us on why we need to use generative models. On the left middle, you see an example of how an inertial flow in a channel with a die of shape, say a square, after passing through a set of pillar obstacles, can reach a shape which is diagonally still a rhombus, but now rotated by 45 degrees. At the same time, if you change, you use the same initial flow shape, but you now change the pillar sequences and how the design of these pillars in between, then you get a completely different shape. And it's not like you just have two shapes, but you can have multiple shapes giving a particular result. While obtaining the forward pass, which is nothing but from the initial shape going to this final shape, is a trivial task with some kind of physics simulations where we can approximate and get the solution very quickly. However, the inverse problem of obtaining a desired shape by designing the channels and designing the pillar sequences in the channel of this inertial flow is the inverse problem, which is very non-trivial to solve. Just to give an overview of how difficult this problem is, we show here how different several samples in this high dimensional probability distribution are laid out. If you look at just the pixel match rate of two shapes, even though they are very close by, there are so many samples which are going to give similar pixel match rate to whatever we desire. And each of the samples requires completely different flow shapes, hence resulting in completely different designs. So this is a many to one problem where often, which is the case in inverse problem, where the forward pass is very trivially defined. Whereas the inverse problem is often very ill posed. In other words, several final outcomes can be reached by one particular starting point, or several starting points can give you the final outcome of the shape. In other words, this shape, which we look at here, can be obtained by different designs of these microfluidic channels. And that becomes the problem of why you need generative model. The generative model generates a whole probability distribution of these kinds of designs, which can now lead to the same shape, whatever you desire. So this is one particular motivating problem which we have been looking at for several years in our research group. But it's not just that generative models are restricted to science and engineering applications. More traditional or canonical approaches for generative models have been used for as image super resolution. So say you start with a very coarse or a very blurry image, and you would like to get more sharp features from by using generative models, then this is another application which has been explored in the past. This is again the generative problem, because several sharp features can give you the same coarse features which we are looking at. So this problem has been addressed fairly well using generative adversarial networks. This is also a motivating factor why we use generative models in our engineering applications. Similar application which has been very predominantly popular in the computer vision community is image to image translation models, where you can take a Monet and then from the Monet you can translate it into an image of a realistic place. Same way, you can take like a couple of zebras over here and replicate the whole image with the background remaining the same, but obtaining horses instead of zebras at that same location. Same way, this is the summer and winter translation. So in other words, what's happening is you are recognizing the features in one domain and you're transferring it to another domain. Our problem of physics based inverse design is also related to this, where you have a set of known values, which is one domain, say a diffusivity in a heat equation or some other parameters. Then from these or boundary conditions for a particular partial differential equation, from there, going to the final solution is one non-trivial task. Now imagine if we have one particular solution and we want to find out what the boundary conditions of that problem is, then it is a much more difficult task. So several such problems of image to image translation and all have been existing in the computer vision community. And then that's the motivating factor of why we use GANs for inverse design framework. The basic idea of GANs is pretty simple. We have a set of data with us, sample data. And from this sample data, we use two networks. One is a D, which is the discriminator, and another network called G. There are two networks, so there are two different pipelines. Let's first look at the pipeline of the generator. What you do with the generator is you input the noise Z to a generator, and this noise Z is a random noise. So in other words, you are mapping your Z random distribution of your Z to a particular solution of your sample space. So from Z, you using a differentiable function G, typically a neural network, this generator G will give us a sampled X from the model. From this X, which we have obtained from the generator, we pass it to the discriminator, where the discriminator will try to say whether the generated sample is realistic or not. If it is realistic, then the discriminator will say that it is close to 1. And if it is not realistic, then the discriminator will say it is close to 0. Now, while this is one pipeline, the other pipeline simultaneously which is used is you have a realistic data set with you, and you sample X from that data set, and you pass it through the differentiable discriminator network. And now you try to ensure that this data set, which is of real samples, these real samples are always considered to be 1. In other words, there is a game which is happening here. The discriminator is going to say all the real samples are close to 1. The discriminator is also going to say all the generated samples. When you're training to the discriminator, the discriminator will try to make all the generated samples close to 0. Whereas the generator will try to make all the generated samples to have a discriminator value close to 1. This kind of a game with the training schematics explained over here, these pipelines, gives rise to realistic looking images. So if you look at in more detail, you have a random vector PZ that goes to the generator, and from the generator it goes to the discriminator, which gives you an output of 0 or 1, and you perform training of the generator using this loss function. And for the discriminator, there are 2 loss functions. One is directly coming from the direct data, which is this log d of x, and then 1 minus log d of g of z is the other training where the discriminator tries to adversarially affect the training of the generator and ensure that it gives an adversarial reaction to the generated training. So this game between the 2% game between the generator and discriminator is the crux of a generative adversarial networks. And once we have trained a generative adversarial network, now you can sample random vectors z, and from those sample random vectors z, you can get synthetic, realistic looking images which come out of it. Some of the examples are shown here. Here are the results obtained from MNIST dataset, and this is for the CIFAR-10 dataset. They all look pretty close to whatever the dataset realistically is. There are more complex examples where the whole scene has been generated from some variants of GAN, which is the least-square GANs here. And several other applications are there where GANs get very realistic looking images, although such examples don't exist in the dataset at all. So this brings us to the idea of how we will use this generative adversarial network in the context of inverse design framework. So we describe a whole framework of network called inverse design networks, or InvNets. Or InvNets also mean invariance based networks. I'll explain what invariances are in some slides later. So this is a framework we will be working on. So before we go further into the InvNet particularly, let's understand what the spectrum of design in inverse design is. Traditionally, inverse design has been performed using either some evolutionary or some gradient-based optimization methods, where you have to parse through several non-optimal solutions finally to reach one optimal solution which satisfies, or multiple such optimal solutions which satisfy the requirements of my inverse problem. This is one extreme. And then over the past decade or so, after the rise of deep learning, several researchers have used supervised learning models for performing the inverse design. And note that for a supervised learning model, you need to generate a lot of data set, And in some cases, it is not even feasible to represent them in terms of a supervised learning model because of the trivial nature of it being many to one problem. Now, for exploring this whole spectrum of design, a couple of years back, several researchers have spent a lot of time exploring the idea of reinforcement learning in design, where you can explore the design space just like how we explore in the evolutionary optimization, but exploring the design space in a much more better manner, and that way explore through the whole design space and obtain the required design. In this tutorial, we are not restricting ourselves by not discussing about reinforcement learning, because there the involvement of physics is much lesser, because you can incorporate the physics information in an environment, and that is a very trivial task. So we leave that for some other tutorial whenever we cover it. But the main focus of our session today is generative models, where we can generate the samples. And as we explained, so supervised learning requires very minimal information. Reinforcement learning still requires a lot of data, but the data here is collected on the fly when you are performing the reinforcement learning is performing its episodes of training. Whereas evolutionary optimization performs a lot of computation, but has very little data storage, and it is very computationally expensive. Now, generative models is one particular like point in the spectrum where we don't need to spend so much computational efforts as we perform in an evolutionary optimization, but at the same time, you don't need as much data as how much we would be needing in a reinforcement learning model. So that is where we place these generative design frameworks at. So with this context, let's look at a problem which we have been trying to solve. This is a problem of inverse morphology design for organic photovoltaic cells. Here, we would like to design microstructures which have high performance or efficiency in terms of the current voltage properties and everything. So for this particular design space, it is again a very large design space with combinatorial combinatorial optimization complexity. And because of that, even a two-phase morphology design becomes very complicated. These are some examples of data morphologies which we would be using in our inverse design framework. But this is just to give us a flavor of how diverse the data set is. This kind of like design framework is like design is performed using an invariance network or InvNet, where we enforce some physics-based invariances to the output of the generative network. In other words, you use the same generative adversarial network, the whole framework of G and D, where G is the generator and D is the discriminator, and you perform these operations. Apart from these, you also include an invariance checker, which will tell whether a particular physical property is matching or not. These invariance checkers could be very trivial, such as P1 or P2 correlation in the case of morphology design, where we check for the size of your grains or something like that, and then use the P1, P2 correlation for comparing and ensuring that the generated morphologies respect a particular P1 and P2 values. So this is one explicitly physics-aware constraint business which we are applying over here. Now, this still uses some training data in terms of the images, but it doesn't require labeling the training data. You just need the set of morphologies, but you don't need the P1 and P2 values for those morphologies. Those are computed on the fly once the generator generates something. Note that for this invariance checker to work well with this generator, invariance checker has to be defined in a differentiable manner. More about this will be explained later on. The GAN types architectures, as explained earlier, we have two generator and a discriminator and then a invariance checker. And these invariance checkers could be either statistical moments or some volume fraction. And just like you perform training of generator and discriminator alternatively, in an InvNet, we perform generator, discriminator, and an invariance checker optimization alternatively. These are some results which we see of how this is the real data, and the synthetic data which is generated from these generative adversarial networks or InvNet satisfies, looks very similar to how the original data looks like, and it also satisfies the target properties which we would like to achieve. So these are some of the results where we can show how just generating one microstructure probably would take around 1.84 seconds. And if you were to perform an evolutionary optimization to reach this kind of shapes, then at least 100,000 such microstructures would have had to be generated and then evaluated. That is around much higher than how much time it would take to even train, at the same time generate that microstructure which we would be using. So this comparison is almost about 3 times compared to what you would be obtaining from an evolutionary optimization standpoint. Now, extending further, this while here we are using some simple statistical constraints such as volume fraction or statistical moments and all, we could use more explicitly defined, user-defined physical properties. In other words, in the case of same organic photovoltaic cell design, the microstructure relates to the current and the exciton distribution in the microstructure, and hence giving a particular current and voltage property for each microstructure. And this whole physics is governed by the excitonic drift diffusion equation with the following constitutive equations. Performing a full physics evaluation for each of these samples is going to take a lot of time. So instead, we come up with an approach where we use the surrogate photophysics model over here, and we define the same generator and the discriminator. Now this invariance checker is going to use the surrogate physics model to obtain the perform the training. So in other words, what's going to happen is, along with the random noise, we send a particular design specification, which is a property of the photophysics property in this case, which we would be desiring. And for those desired properties, you generate a set of microstructures. And for these morphologies or microstructures, we send it to the surrogate photophysics model and perform an invariance checker to ensure that the design specifications match whatever design specifications or photophysics properties we obtain for these generated microstructures. This, along with the discriminator, is the total InvNet framework which we have created. The advantages of this is that one, we have a very fast generator of these microstructures. At the same time, we use much lesser data, and we are able to use surrogate physics models for getting physics aware inverse design framework. This is a work from our group. Having said that, there are several other research groups working in the same area and working in similar topics of how to do inverse design using generative adversarial networks. The flavor of the problem remains the same. How we define a generator and a discriminator and a surrogate physics model. However, the physics itself which we are solving could be different. While we are solving for photophysics, other research groups could be focusing on fluid mechanics or other kinds of design problems, which are very interesting. We also look at how we get this full fidelity surrogate physics model, and we also use something called as a multi-fidelity surrogate physics model, where we use much lesser amount of data than whatever is needed for a full fidelity surrogate physics model. And that way we are able to obtain much faster training with much lesser data set requirements. The multi-fidelity surrogate physics model also, for it to work very efficiently, it uses some low fidelity label generation, which comes at no cost or almost very minimal cost. This forms the crux of the multi-fidelity surrogate physics model. These are some of the approaches which several researchers have been using in this physics scientific machine learning area, on how to reduce the data requirements and how to reduce the computational requirements, how to perform get convergence of the results and all. So these are several aspects which we would be we are explaining over here. Again, we also look at in terms of comparison of how JSC and InvNet, like how much time does it take to evaluate the physics simulations compared to the full physics simulation, which would take probably around 10 minutes. The physics simulation, if a surrogate physics simulation will give us results in less than 50 milliseconds or something, which is way faster than what we would be using. And then the InvNet training could take almost about 20 hours. But then the morphology generation for a particular desired property is 192 milliseconds. Whereas with the just the physics model, obtaining this inverse design is next to impossible. That brings us to the question: can we avoid data generation completely? Yes, by using diffnets, and that is the idea which we would be pursuing in future. So in concluding remarks, in this presentation, we introduced how generative adversarial networks is one of the design frameworks which we can explore in the whole spectrum of different approaches for inverse design. And particularly we look at that GAN-based inverse design framework InvNet used for microstructure design as a particular application. With this, I'd like to thank you all for eagerly participating in this tutorial. And if there are any questions, please feel free to either leave us a chat message, or you can always contact us in our email IDs. Thank you.